before that, first thing about cut-off region means that it is off. What is the condition that you turn off the transistor again? Very good. VGS less than VTF. Thank you very much for participating, everyone. Right? Done. Easy. Then last time we derived the equation, we did not really derive, right? I just tell you how to find the charge, how to find the velocity, what is the current, how the current depends on the charge and velocity. We did not derive it. You can take any textbook and derive it if you want. But anyway, last time we derived this, we came up with this equation that I equal to W on L mu C ox times VGS minus VT, the whole thing times VDS minus VDS squared divided by 2. Right? I'm very familiar with this, right? I don't need to read the cheat sheet because I work on this for decades. I really can say decades, my God. Yeah, but right, so this is what you have. Under what condition? It's under when it is not pinch off. So we just say that under what condition would it pinch off? It is when the, yeah, of course, I do need the VGS larger than VTH to turn it on. But at the same time, I also require VGS, or this time I don't want to use VGS. Let me just say, I want to introduce VG minus VD larger than VTH. Okay? And what is VG minus VD? I want you to be familiar with this. Whenever I say VAB, it means VA minus VB. Potential is meaningless without reference. Okay? I can say I have potential energy of 1 trillion joule. That is fine. But if everything else in the world is 2 trillion joule, I still have less potential than the other. Okay? So it must be a relative one. So when I say VG minus VD larger than VTH, that means VGD larger than VTH. Okay? Am I right? I think so, right? Where's my cheat sheet? Yeah. But maybe I should also say another thing. Actually, this is not usually what you will say. We will reference to, let me just, I did not write this well. I want to reference to, I can also write this as VGS minus VDS larger than VTH. Correct? Because I just referenced this to S, right? The S will get cancelled. Yeah? And then it means VGS larger than minus VTH larger than VDS. Right? So they have all these things. Yeah?
Sorry, which one was VS?
Yeah. VS is the source. It is the lower potential. So this is VS, this is VG, this is VD. Yeah, thanks for asking, right? Because I assume I've been teaching device physics, so I assume everyone knows, but this is not the case, so please do ask. Now, do you see how I come up with this? How do I memorize this? Not really, I try to memorize this. I remember that I can form a channel on the right-hand side. That's why VG minus VD need to be larger VTH. It's just like when it is on, I have VG minus VS larger than VTH. That's how I memorize it. Right? So if you can think it as forming a channel on the left and right, this equation is easy to memorize. Now, however, once we enter into pinch off region, right, which we call it saturation, what will happen? You think about this. I derive the equation for this one, right? This one, I can have the equation here. But once I pinch off, all it does is just keep shifting this pinching region to the left. This one, right, if you ignore the shifting here, this one is exactly the same as this one. Do you agree with me? From the drawing point of view, at least. If you assume L1 to L distance is very tiny, this picture is exactly the same as this. So if I keep increasing VDS, if this is still very tiny, I should have the same current, right? Because they're exactly the same, just look at the drawing. The only difference between these two drawings is that I have a gap here. But let's assume this gap is very tiny. Then when you solve the equation, because this is 1 volt, right? I don't care about this part. This part is the waterfall. The flow, how fast my river flow has nothing to do with the waterfall, actually. It really depends on the slope here, right? The waterfall is just eventually you go to the sink everything go, right? So because of this, I can say that when VGS minus VDS larger than or equal to VTH, then I have a constant current, which is 0 I W on L mu C ox times VGS minus VT. At that point, when I just pinch off, I know that VG minus VD equal to VTH, right? When it just pinch off. So I can substitute this VDS as VGS minus VTH. Then the whole thing minus VGS minus VTH squared divided by 2. I'm just using this equation and find its current when VDS equal to VGS minus VTH. Because when VDS equal to VGS minus VTH, it just pinch off. Any question about what I'm doing? Right? And so, this one, you just simplify it, you get W on L mu C ox divided by 2 times VGS minus VTH squared, which is independent of VDS. So now if I have want to draw the current as a function of VDS, before when VDS is smaller than VGS minus VTH, I have this so-called linear or child region. The current increases when I increase VDS. But after that, I have a constant current. Okay? Yeah, forming, so does that make sense? Or? Just ask anytime, right? Yeah, but no. So the point is, in this class, I'm not going to test this, right? This assumes the foundations, but I want you to understand because we're going using the concept from here to derive some more important concept. So if you can understand that, it's great, go through the derivation. If not, you might need to take it for granted. Then we go to the next step. Yeah. Which is reverse. This one.
Yeah.
Of course, this is a typo. Huh? Yeah, of course, this is a typo. Thank you for pointing this out. Like this, right? Thank you, right? So my mistake. Yeah, and that is exactly what it is saying here. VDS, if you rearrange it, become VDS to the right, then VDS is larger than VGS minus VTH. Okay, this is called IDVD curve. Any questions? Okay, anyway, now the point is that you could be good if you try to understand some of the physics. If not, you need to memorize this. You have linear mode and saturation mode and cutoff mode, okay? Now then, in device physics, you always will be asked to plot 2 types of curve. I give you a transistor. One is called IDVD curve. What does it mean? I want you to also appreciate this. So IDVD means that I want to plot the drain current as a function of drain voltage. That's it. So memorize it, IDVD. Okay? Now, however, if you look at this current, this equation, it also depends on VG, right? the current depends on VG. Make sense? So how do I plot this curve? For example, here. So IDVD will be something like this. This is not a good drawing. Okay. What does it mean? Of course, when the drain voltage increase, the drain current increase, right? Then why I have different curves? Why people show different curves for one transistor? Yeah. For different VG. Very good. Yeah. So this might be VG, and to be clear, I am going to say VGS minus VTH equals to 1 volt. For example, I overdrive by 1 volt. This might be, so I'm not drawing to scale. VGS minus VTH equals to 2 volts. Okay, now some of you may complain, I want to remove this one and then redraw this one so that you understand why I say some of you might complain. What if VGS minus VTH equal to 0? Equal to 0. No current. That is the third curve. Do you see that the spacing is different? That is expected because they depends on the square of the VGS minus VTH, right? So that is why I need to redraw it. I did not draw it well. And again, on this region is the saturation region, and this region is the linear region. Okay, that is the first thing I want to say. We will keep seeing this curve in the future, so we need to practice. Another type of curve is called the ID, and naturally you will say VG, right? What if I plot it as a function of VG? What should I expect? I will expect something like this. Make sense or no? Why? What is this point? VTH. Very good, thank you. Because you just turn it on. And again, you will see that bad choice. It might give you two curves. Okay? Why we have two curves again? I mean, why I have different curves for the same transistor? Because it depends on VD. So this might be VD, and let me redraw this because I did not draw this in the right scale. So this might be VD equal to 50 millivolt, very tiny. It's just a linear. It depends linearly on VGS, right? And this one might be VD equals to 2 volts. It go up quadratically. Is it quadratically? Yeah, right? Because now you are in the saturation region, right? And I just want to tell you that in reality, that's not what you see. You actually will see something like this if you keep increasing VG. Okay, so this one we will study later. This is because of the contact resistance. Now you have a very large current. This current need to pass through the contact of your transistor. Those parts are dominating, so it does not go up as fast as you want. Another is the so-called surface roughness, which we will study later. When you have a very large VG, you push the transistor against the wall of the insulator. So they have a lot of scattering. They lose their mobility. Okay, I will explain more later. But you just say that in reality, this will taper off. Right? I will keep repeating, but any question now?